For us to start. So now let's begin. Welcome to another Microservices Meetup. And I want to start by thank you to AutoScout24, my ex-employer, and I've seen also some colleagues around helping with the camera. So I'm very proud of my ex-company that they are still sponsoring the meetup, despite me having left there, but nevertheless the original idea of the meetup is still worthwhile sponsoring, paying for pizza and beer. And if you want to give back to a company who is doing such a cool meetup, they are still hiring as far as I know. Are they hiring? Yes, they're hiring. So give them a chance and contribute to a cool culture and a cool company. Besides that, I pinged Lorenzo after I saw this talk at a conference. I have not seen it. I've just seen the abstract, and I said, "This is cool. I will just ping him." And then he answered back, "If my company allows me to go there and pays for that, I will show up. I'm from London. I need to fly in." I said, "Cool." So you're just flying in to give a meetup presentation because you want to give back to community. This is great stuff. And the topics in there are all my buzzwords currently. So there is event sourcing in there. Of course, I also like the think later part. This is and now, as I'm moving into the IoT world, this seems like a perfect introductory talk to my new journey at my new company. So give a warm welcome to Lorenzo Nicora, and I assume you will introduce yourself.
Yep.
And enjoy the presentation. Thank you.
So, first of all, thank you for inviting me to this meetup. When I wrote this title, I realized, as Christian was saying, probably I exceeded the limit of buzzword per title. But you will see, this is actually the subject. So, about myself. Let's see if this works. So, as Christian was saying, my name is Lorenzo Nicora. I'm originally from Italy, as you probably guess. But I'm now living and working in London. I've been living there for the last 3 years, working at the moment as a platform engineer lead in a consultancy that is called Build It, part of a bigger consultancy that is Wipro Digital. I've been doing microservices, or let's say distributed systems. So before, people used to call it microservices, for 7 years, something like that. Cloud native system, cloud native application, mostly AWS to be fair, not much other cloud system. Event-driven architecture and reactive. My main language as a developer, my main background is as a developer, is Java, but I also use many other languages. In the recent year for microservices, I used a lot Spring Boot, works very well with microservices, but also in Java I used Akka with actors, that's interesting, and more recently serverless in Node.js and TypeScript. But this speech is not language related or framework related at all. So we are going to talk about event sourcing. I guess many people, I'm getting out of the light just to see you. How many of you are familiar with the idea of event sourcing? Could be, okay, many, I would say most of you. How many of you are using event sourcing in a real application, let's say in production? Okay, not many, but some of you, 4 or 5, something. Out of you 4 or 5 who raised the hand, how many are using an implementation of event sourcing based on domain-driven design? No? Curious? Interesting. This is interesting, and most of the people, maybe you're doing without knowing, but this is interesting. Most of the people used to use an implementation that are at least implicitly based on domain-driven design. But let's go on. So, some assumptions, some base point of this talk. We are talking about microservices. Well, considering the meetup we are in, shouldn't be a wrong assumption. So we are talking about distributed system. Microservices should be distributed system, are more than this, but they are distributed system. We are talking about systems that communicate, services that communicate each other, either synchronously with a request-response pattern, HTTP usually, or whatever, or asynchronously with a message pattern. And we are talking about systems that are supposed to scale horizontally, so just adding peer nodes to scale out. Not you scale out and do not scale up. You do not make one service fatter, you add more nodes. And the second, well, it's an assumption, is a base of this talk, is we need to scale. And we need to scale keeping the latency low, reasonably low. So it's easy to scale growing latency, but we need to keep it low. So let's start from the way we used to do, or we are still doing, persistence. Let's call them legacy persistent. It's not necessarily legacy. It works very well in many cases, but it's the usual way. So we have a single application. Well, it could be monolith, it could be also distributed, but it doesn't really matter. It's a single application that processes both writes and reads, so both updates and queries, through the same code base in a synchronous way, request response, and interact with the relational database through transaction, ACID transaction, and each write goes to update the state of our system in the database. So we are directly updating the state. And we are using exactly the same data store for reads and for serving the queries, for serving the reads, queries, every read we are doing there. But at some point we need to scale. We need to serve more requests. We need to serve more clients. So, well, one strategy, the first one that could come to our mind is scaling out the application. It's the easiest thing to do. So we have multiple nodes. Let's concentrate on writes only at the moment. That's the most critical thing to scale out. We have more applications still working exactly the same way, request response, still updating the data store. The data store has to be a single one. We cannot distribute it if it's a relational database. But here comes problem. Here comes problem as we are writing into the database in a transactional way. Transactions implies locks, that implies contention if you are doing concurrent writes. And as our application is synchronous, works in a request-response way, we are actually blocking our response until the database confirms the write. And this harms the throughput of the latency. So reduce the throughput and increase the latency. And things are not going to improve when we scale out, are getting worse, or say the same at the best, as signal propagation is just adding more latency. So we add more nodes, we have more communication to synchronize the system, we're increasing the latency. And the critical point is the database, regardless the number of nodes we add, the database is still our bottleneck. So why not trying to do one more step, using the reactive concept, the concept behind the reactive manifesto. If you are not familiar, I would invite you to have a look. There are a very interesting concept. They are behind the reactive system and reactive programming from different point of view, different aspects. Summarizing very briefly, it means if we want that our system, if our system has to be elastic, has to scale out as needed, but keeping it responsive, so keeping the latency low and also be resilient, the system has to be message-driven, has to work asynchronously. This is the idea behind the reactive system, reactive programming. So let's go async. Let's transform our system in a message-driven system. We are concentrating again on write. So we have multiple nodes receiving the updates from our client. We are treating them as messages. We might put a messaging system, a message broker, a streaming system, Kafka if you're using something modern or something other there, and then we are going to apply the updates in the same database. We are not changing the database so far. This system could scale out better, actually, as one thing is our messaging system could act as a buffer if we have peaks here. We are not blocked by possible delays on the database, but also if we are using some proper, reliable messaging platform, again, I'm mentioning Kafka, but there are many out there that are not only distributed, but they are replicated. So when we send the message to the messaging platform, and the message platform acknowledge it has received and possibly replicated the message, we are sure it's not going to be lost. Effectively, our write latency is just this one. So it's just from receiving the update, sending to the broker acknowledge back. This is still synchronous at the moment, or might be not. We acknowledge back, this is the write latency. And then the actual write on the database could happen later. We are sure we are not going to lose these messages. Of course, we have to handle retries properly if a write fails, but this is fine. This is potentially, this scales better. But we are still updating the state there. We haven't changed the way we are managing, we are storing our state. And there is a problem there. And the problem is the order we apply updates matters a lot. If we have a number of updates on the same part of data, of the same piece of data, and something happened, so our updates get applied in the wrong order, we end up with the wrong state. And any distributed messaging platform cannot actually guarantee in an absolute way, so end-to-end, not just inside the broker, cannot guarantee the absolute global order of messages. But the real key point here is when we are updating the state, we're actually losing information. And if we find out that we made a mistake, something went wrong, we cannot reconstruct consistency at that point. We have lost information just updating. We apply the updates in the wrong order, that's done. After that, we find that it was wrong, okay, we don't have the information to fix it. So why not trying something with double quote, it's absolutely wrong, but let's try naming it update sourcing. So the idea is we receive the update, and we treat them as messages, and we store them as they are. In a log structure, it means append only. Just we save the updates as they arrive. We store all of them, we are not losing them. And then, in another part of our system, we use these updates through some form of business logic to rebuild the state. And we use this second part of our system to serve the read. And the advantage here is, if we find the state was wrong, there was an inconsistency, there is no problem ditching the state and then retrieving the updates, replaying them, and rebuilding the state after having fixed the problem, after having reordered the updates, for example. So we are not losing any information. And here we are implicitly applying what is called CQS or CQRS more recently. So it's command and query writes and reads, updates and reads separation or responsibility segregation. So we have two separate parts of our system that takes care of the writes and of the reads. But doing this, we have dropped transactions. We have dropped ACID transactions. But well, we still have to enforce consistency in some way. So where we are enforcing the consistency? Well, the usual approach, the usual answer that comes from the domain-driven design is using the concept and the implementation of an aggregate. The aggregate is a cluster of domain objects that actually works as a single unit from the persistent point of view, but it's also our unit of consistency. It means that one aggregate as a whole moves from one consistent state to another consistent state, never ends up in an inconsistent state by definition. And this is also essentially the boundary of our transaction. And the typical example everybody is using is the e-commerce aggregate. The e-commerce order, one e-commerce order. So one instance of an aggregate is one specific order with one ID with all the parts that compose the order. Sorry. So the domain-driven design approach to what I call wrongly update sourcing is actually something like this. So we receive a signal, we are calling commands. Bear with me for 1 second, I will talk about commands and event later. So we received signal from the client, we call commands. We have an aggregate that is stateful, that is absolutely stateful, that apply the command. If the command is correct, if it doesn't break the consistency of the aggregate, the state of the aggregate changes. And the aggregate emits the event, and we store the event in our log structure, append only. And when we have to rebuild the state of this aggregate, we just replay all the events back through some business logic, and we have the state back. The idea is the state is always represented by the sum of all events. So I introduced the idea of common and events. So what are common and events? The idea is actually very simple. So a common is a request coming from our client, for example, is like submit this order, this specific order, is a phrase, an imperative. It's something that will happen, probably, but might also fail, might be rejected for being inconsistent for many reasons. It's a request again. It's not something that has happened. While the event is something that has happened. It's a phrase at the past tense. And the difference is important. This is a request. This is a statement of something that has happened. As something that has happened, it cannot fail. It already happened. Unless you travel back in the past and you change it, it has happened. And cannot fail, cannot be rejected. And the idea at the base of the aggregate, receiving commands and emitting event, is that the aggregate, one instance of an aggregate, so the representation of one e-commerce order, one instance, not the code, is stateful, as the consistency, keeping the consistency depends on the state, and one instance is single-threaded. It doesn't mean the code of the aggregate is single-threaded. It means each aggregate instance has to process one command at a time. Interestingly, this aggregate behave exactly as actors from the actor model, from the actor programming model. I'm not talking about actors. I invite everybody to have a look if you're not familiar. It's a very interesting concept. Maybe you're not going to use it, but when I learned about them, they changed my way of approaching code, even when I'm not using them. But let's part the actors. So what happened in our system? When we receive a command that refers to one specific aggregate, if we are lucky enough to have the state of the aggregate in memory of our system, okay, that's simple. We just apply the command, the aggregate decides whether it's correct or not. Let's say it's correct, it changes state, emit the events, and we save the events in the event log. But what happens if we receive another command referring to an aggregate that it's not in memory at the moment? We have it in the event store, but it's not in memory. Well, in this case, we have to replay the events, retrieve them from the event store, replay them, recreate the final state of the aggregate, and only at this point apply the commands. The aggregate will emit the event if the command is consistent, and we will store it in the event log. This could take a while. And also, imagine, okay, we are talking about a distributed system, so we have many nodes. So one aggregate will live in one node. Cannot live, we said we have to have one instance of an aggregate, as one specific instance of an aggregate, sorry, one instance of each instance of an aggregate. We cannot have many copies of the same e-commerce order in many nodes. So that node should live just in one, that order should live just in one of our nodes. And we should handle it. So if we have a system that has multiple peer nodes handling this part of the process, and aggregate lives in different nodes, we have to decide some form of sharding, some form of a distribution of we have to partition our aggregate with some logic, with some deterministic logic. But it means that we have to put one additional stage before to route the request coming in. We are talking about distributed systems, so we have multiple nodes of everything. So every command that comes in has to be routed to the node processing that aggregate. And we have to face different problems. When we scale out, we have to repartition the data, and this could take time. As anybody who has repartition data in a Cassandra cluster or a Kafka cluster knows it takes time, it's a critical moment. There are also different solutions, not the only one. We could decide to use some form of shared in-memory data store, like Hazelcast, to name one. It works very well. This allows us to have the state in the shared data store, but we still have to synchronize the processing of the commands. So we might route the commands to any node, but then we have to have some form of global pessimistic locking using this data store to have just one node processing the command for one aggregate at a time, or some form of optimistic locking, but then we have to handle retries, and we are still sharing the state, and sharing means hops, network hops. It's not for free. And everything, all these things are adding latency, especially, well, we are talking about write, are adding a lot of write latency. Let's park the writes for a second. We will come back later. But what about reads? But we still have queries. We still have reads. Well, when we have to retrieve the state of one specific aggregate, well, a naive implementation like we receive the request of retrieving the state of that order. Okay, our system retrieve all events of that specific order, replay on demand the events, rebuild the state, and return the state. This is a naive implementation. It's not very efficient, but could work unless the aggregate is built by thousands of events. But in a basic situation, could work. But when we are talking about querying, having a naive implementation like, okay, let's retrieve all events of all possibly matching aggregate, all possibly matching orders. Let's rebuild the state of all these orders, let's say in memory or somewhere. Let's run the query against those states to retrieve the few matching our query and return them. This is not a matter of not being efficient. This simply doesn't work. I mean, it's absolutely crazy. It's not realistic. So the approach, the general approach, is using what are usually called read models or views. There are different names for them. I prefer to use the concept of read models. The idea is when we are receiving events, the aggregate is here. So here, these green boxes are already events. We are storing them in the event log, and, well, possibly in parallel or downstream the event log, we build images, pictures of the state or the aggregate in some form of store that are designed to serve queries. And these read models could be persistent, could be not. But the point is, these read models are conceptually weakly persistent. These read models are not our source of truth. Our source of truth is the event log. And at any point, for any reason, an accident or we have to change it, we could destroy this and rebuild them, replaying all events. So this might or might not be persistent. This might be built on demand or directly streaming the events. But the point is, these are not the source of truth. That is the source of truth. But another characteristics of read models is we don't have one read model per aggregate. We don't have one read model for the e-commerce order. We may have many. We will have many of them for serving different type of queries against the same aggregate, the same idea of aggregate, possibly using not only different data schema optimizers for different queries, but also different technologies. Could be relational database, could be index service, could be key value store, whatever. But the point is, the idea is you have many of them specialized for specific read use cases. So the read models, as we describe them, are a representation of the state of our domain for doing many things, for all the things we need reads. So for the UI, for supporting user decisions, building, showing the UI. For external systems that are interested in the state of our domain, for other microservices in our system. And read models are, as we said, based on events. So are based on things that have happened. This was the definition of event. But where the things happen? This seems trivial. This seems stupid as a question. Actually, in the usual implementation of event sourcing, with the aggregate receiving command from the external world, emitting event, things happen inside our system. We just receive a request, but the things happen here. And this is necessary for enforcing invariance, so for enforcing transactional consistency at right time. This is our right. So our write happens after this. If we handle the event to our messaging platform, our secure messaging platform, our write time ends here, just after the messaging system acknowledge it. But we are enforcing consistency on the write, so we have to wait for this process happening before we may acknowledge the write. And this is the base of the idea of the aggregate, of this implementation of the aggregate, as it's the aggregate with its state that had to decide whether the command is consistent, so the change that is going to happen is consistent, so emitting the event, or it is not, so rejecting and not emitting any event. And this is the usual, oversimplified of course, the usual implementation of event sourcing most of the people are using. It's fine, there is nothing wrong with that. This works very well with very process-oriented domains, with domains that are very transactional by nature, that require strong consistency. Not by chance, all the examples you see around are based on bank account, e-commerce. Actually, e-commerce is kind of flawed. If you know Amazon, if you're using Amazon, it's the most eventual consistent system I know. But, well, people still think about e-commerce as very transactional, as a simplified model. The key is, this system works very well when our system, is in control of the process. So our system is the controller of the process. Okay, and it's fine. In many cases, this is true. So there is nothing wrong with that. But the point is, there are also different kind of problems. There are different kind of domains, and there are domains that have different type of problem. There are many domains where we are not driving the process. We are just collecting external events, so things that happen somewhere else. We are receiving the signals, and we are collecting them and doing something with them. We cannot say, oh, this hasn't happened. The courier hasn't delivered the parcel. Well, we received the message. We cannot say, oh, he hasn't delivered the parcel, because that parcel wasn't in the right state, so he's lying. No, he's not lying. So something went wrong, but we received the signal, the courier delivered the parcel, and that's it. We cannot reject it. Also, and this is orthogonal, they are not necessarily correlated. There are also many domains where the sources of the events are kind of unreliable from different point of view. Or at least the transport, the network that send the event to us, it's unreliable. And these three things, let's say two, the unreliability and the type of domain, are not so exotic. As the domains where we are gathering something that happens, there are more than this, but logistics and trackings are typically this kind of domain. We are tracking events that happen. We cannot again say the car is not there. It jumped 3 kilometers. Okay, something was wrong for sure, but we cannot say, oh, it's wrong, it's inconsistent. So we have to gather this information and try to make sense of them. And from the unreliability point of view, well, in many cases, IoT and mobile apps are, at least for the network, in this case. Mobile application could work in, well, by definition, the mobile network is not reliable, is not completely reliable. Could be delayed, could be off. The application could work offline and send the message later, could be temporarily disconnected, and so on. But the key point in terms of the domain is, in this kind of problems, things happen in the external world, not in our system. And what our system is trying to do is trying to draw a picture of this external world and trying to make sense of it. That's the idea of this kind of systems. And we are receiving messages from these devices, but these messages could be delayed, could be lost, could be delivered minutes after or hours after they happen, when the mobile application reconnects. And when we receive this event, we cannot reject it. It has happened. So the idea of receiving commands, enforcing consistency, possibly rejecting if what we received was inconsistent, cannot really work. And the problem is this model here relies on the fact of receiving all commands in the right order, as they usually represent change in the state. And if the change in the state happens in the wrong order, it's probably inconsistent. And also, it relies on receiving all commands. But we just said that we could miss some of them, as the network simply is not delivering, hasn't delivered that for any problem. So for this kind of problem, we have to just give up trying to enforce consistency at this level, at the right time. And this means dropping the difference between commands and events. And this means we are receiving this signal from the external device. We write them essentially as they are. Simple validation, possibly. Authentication, that's a different problem. And what we do is we put an effort in trying to make sense of them, trying to rebuild consistency later when we build the read models. I named, with a colleague of mine actually, named this approach write fast and think later. As we are receiving the events, we've made a very simple validation, very basic, store them, written, so write fast, and then we apply effort here, we apply business logic here to build these read models as consistent as possible. The switch in the mindset from the first model, the domain-driven design approach, commands, stateful aggregate, consistency on write, events may be rejected if something was wrong, and this approach is not distant logically, but it's at a different level from the switch of mindset you have to do when you switch from transactional ACID relational databases to the base approach that is used for all the distributed NoSQL databases like Cassandra, DynamoDB, this kind of data store, this kind of modern data store. They are designed to be to scale out, but they are not transactional. They are always eventual consistent. So what happened to our system, to our event sourcing system, is we don't have the distinction between command events. They are all events, as they happen somewhere else. We are receiving events, effectively. We still have a phase of validation, just to avoid to store forged messages, someone trying to send us messages, well, just to trick our system, malformed messages, completely malformed messages, or something like that. But there is no distinction. They are still events. We are just validating them. And the point is, this validation here, it's completely stateless. There is no need of processing one at a time, even for one single aggregate. We might process it in parallel. It's not stateful. And this is extremely efficient for scalability. As our system, any node in our system could process any incoming events. If we have to scale out, we just add nodes. Any node could process any event. And beside this model, in this model, the event log could also be stored, maybe not in a relational database, it still works, but could also be stored in a distributed key value store or key value store, like, again, Cassandra, DynamoDB, that is usually designed to scale. So this model scale out a lot, and it's able to cope with huge write peaks, concurrent write peaks, much more than the other approach. And this approach implies not trying to make sense of the events that are coming in at right time, but trying to build consistent read models. It's swapping the approach from the usual event sourcing. And this is not a problem, trying to build or rebuild consistency in the read models, as we can rebuild, as we said, we can rebuild the read models at any point when we spot inconsistency. What it means? What does it mean? Well, we might decide with this approach to reorder events. They came in the wrong order, and we might have to reorder them when building the read model. We might guess missing event that have never been delivered. We might decide to rebuild read models if we receive a late event. It's something that has happened 1 hour before, get delivered 1 hour after, just as the mobile has reconnected to the network. We might decide to ditch the state in the read model of that specific aggregate, ditch it and rebuild it as we received a late event. We may also decide to forcibly and willingly delay read models, just to give time to events to arrive. Or, and this is kind of the same thing, applying the concept of watermarks. The concept of watermark comes from a white paper, I think it was from Google. The idea is when you're building the state of something from a string of messages or of events or messages, let's say messages, in a streaming platform, these messages takes time to propagate to you, and the time that each message takes is not known. So you never know how long it takes from a message to reach your system that is rebuilding the state. So the point is, one point is you're always looking at the past, of course, that as the messages takes time to reach you, but you cannot look close in the past. You have to put some limit depending on the expected propagation in your system, the estimation of the propagation in your system. Let's say I'm just making it 1 minute. So you ignore the events that are more recent than 1 minute. You are building the state of the system just 1 minute back. So you are always looking back in the past, and beyond the watermark, beyond this limit, you decide, depending on your use case, depending on the propagation of the message in your system. This is a very general concept. It doesn't apply just to this approach, but works very well in this approach. So you might decide to forcibly delay read models of minutes, seconds, it depends, to give events time to arrive. The idea of guessing missing events is not so crazy. I reckon this has been thought for a conference in London. So this is based on the TfL, the transportation company, managing the underground and the buses in London. So what the TfL does, you can travel with the contactless, with a credit card, a contactless credit card. Has to be issued in the UK, but it works. So what you do is tapping when you get into the station, and you tap again when you exit the station. So they record the travel during the day. But what it happens very frequently, well, not very frequently, but frequently, that one tap just get missed. Maybe the reader wasn't working, or there was a huge crowd flowing through the gate, and you just missed tapping. This is not a problem, as the approach that TfL is using, they never charge you in the day. They wait at least 24 hours, so they wait after the midnight, sorry, not 24 hours, they always wait after the midnight, and then they try to reconstruct your travel during the day, and they guess the missing thing based on your previous travels, or the other station, or so on, and they are, I would say, very good in doing that. So many times you see, if you check the state during the day, they say, oh, this is missed. After a few minutes, so after an hour, you say, okay, we guessed you were actually traveling there. This is exactly guessing missing events. These are the events. This is an event-sourced system for them. They are receiving events, tap in, tap out, tap in, tap out, and they guess missing events. And how they do it? They wait. They wait until midnight, at least, a bit more, actually. This is just an example. It's not something crazy. Building read models this way is expensive, of course. It's not trivial. It takes time, takes processing time. But we are talking about microservices. And actually, the work of processing writes, serving queries, and building read models could be handled by separate microservices. And I would say should be handled by separate microservices. And so they might scale completely independently. Also, as we are talking about messaging, the interaction between the services is asynchronous, so there is no time coupling. It's not a problem. We might have a peak in the write, we have to scale out temporarily the services handling the writes and building the read models. This is fine. This is not harming the performance of the reads. Or we are delaying the writes, so we have the peak in the writes, and then after sometimes as we are willingly delaying building read models, the peak in building read models is slightly delayed. This is not a problem. They are separate systems. Even if they overlap, they're a separate system. One process is not interfering with the other. One key point, cannot be, you cannot work around this, is read models are always delayed. Milliseconds, seconds, minutes, depending on your model, on your domain, the possible delay or the transport from the device to your system, but they are always delayed. So we said this approach allows us to reorder events when building read models. But what is the right order for events? This looks like an obvious, a stupid question. I mean, it's obvious. The order of the event is by timestamp. It's obvious. Yeah, but which timestamp? Well, in this kind of system, we have many timestamps, not just one. We have multiple timestamps inside our system. Just for example, when we receive, when we process, when we store, they could be milliseconds apart, but they are different. But we said things happen externally, not in our system. So these timestamps are meaningless. Also, we said the transport is potentially very unreliable. So these are completely meaningless for the ordering. We could use them to do some guess, but we cannot base the ordering on them. So the reality is the only meaningful timestamp is a timestamp put on the event by the source, let's say by the device, if we are talking about this kind of system, is by the device itself. Let's call it event timestamp. There is no unique name for that, but that is the timestamp. Well, of course, it would be very nice having an atomic clock on every device. Would be perfect. So every timestamp will be perfectly synchronized. Okay, we are not handling GPS satellites. They are perfectly synchronized. Unfortunately, our system is not receiving event by GPS satellites. And clocks of our device will be skewed. Even if they synchronize their clock with the internet, they will be skewed. So we may rely on the clock per device only. So we cannot rely on different clock-based synchronize, but we could reasonably rely on the fact that one clock of one device is coherent with the self. In many cases, you are lucky, and in your model, your aggregate, here I'm talking about not the implementation of the aggregate, the idea of the aggregate. It's a more general thing. One aggregate is one-to-one with one event source, with one device. So you are kind of lucky in this case. Frequently, this is the case. So you have an easy event order. So you use the timestamp put by the device, and that's a reliable order for your event. Sometimes you are less lucky. And the aggregates that represent your domain, the messages, the event that refers to aggregates comes from different devices. There is no one-to-one relation. Different mobile send messages referring to the same order. Okay, wrong example, but could be something like that. In this case, there is no easy and completely reliable event order. There is not. There is no workaround. You don't have a reliable global event ordering. In any case, in this case, you have a kind of reliable local ordering. In this case, you have to guess. You might try to reorder events using causal consistency, using causal relation between events. So you know that one thing has to happen by definition as the rule of the world before the other. You receive events in the other way around, so you might reasonably guess that actually you receive the first message delayed, and you may reorder them. But usually this is not as trivial as it is. But this is a strategy. This is a possible strategy. So wrapping up the idea, putting all things together. When we are talking about distributed system, specifically microservices, when scalability is critical, and when I would add when you have to cope with huge amount of data, but you have to keep especially write latency low and having many concurrent write, and when your domain fits event sourcing, and this is the case of many domains, well, you have two possible approaches. One is the domain-driven design approach, still works very well. Command, stateful aggregate, event log, rebuild the stateful aggregate for event. This way you are applying transactional consistency at right time. As we said, with this model, things happen inside your system, not outside. Our system reacts to requests coming from the outer world, but our system is driving the process. It works very well with process-oriented system when you need strong consistency, but doesn't cope very well with external unreliability. Typical example, network unreliability. You may have problem if commands comes in the wrong order. You end up rejecting legit command that just has to be delivered later. And in many cases, if you have to scale out hugely, this doesn't scale out so well. Or better, doesn't scale out keeping concurrent writes latency low. But this case here of external unreliability and scaling out, as I said, is not so crazy. It happens to us when we are building a parcel tracking system. So in the morning, couriers wake up, they all scan the parcel, so huge peak of concurrent writes, and we have to cope with that. In that case, that model didn't work, so we decided to use this second model, the weak write consistency, what we call write fast, think later, just a name. The point is, lenient and stated validation on write at right time, no distinction between commanded events, all are events, we are just validating them. And then enforce consistency later and try to build consistent read models. In this approach, things happen outside in the world, not inside your system. And the job of our system is try to make sense, try to draw this picture of the world and try to make sense of that. It's completely different. The advantage of this system is scale out very well, and write latency could be very low. Copes very well with external unreliability. You may put measure in place to reorder event, something like that. The main drawback is read models are always delayed, but often are not a problem, or you have to cope with that. And of course, you cannot in any way, with this kind of approach, have any form of write time transaction. You could do that with the other approach of event sourcing. You cannot do that with this approach. But with this approach, we said we are not driving the process. So this is not really a problem. We are gathering events. So there is no point in rejecting them. The point is, the second approach might look crazy, but is not so crazy. The word is eventually consistent by definition. If you think the word we are working on, we are living on, is eventually consistent, is never transactional. And the word we are working with, we are living in, is unreliable, and we are always looking back in the past. We are never looking at the present. So we are always building in our mind a picture of what happened, even just for the finite speed of light. Okay, it's a different thing. So the approach you have to take generally is, I'm quoting Jonas Bonner, one of the authors of the Reactive Manifesto, you have to guess. If something was wrong, then apologize, and then taking some action to compensate. Not try to be transactional, logically transactional, not just database transactional. And that's it. Just credit to a colleague of mine I'm working on that. In this presentation there are many ideas of his. I hope I gave you some useful idea, possibly. Happy to answer any question, to discuss. That's it.
Thank you very much. So for questions, I'm running around with the microphone again. Yes, in the back. You want to see me running.
So during the start of the presentation, you mentioned the evolution of systems which transition from transactional to more event-driven stuff. Mm-hmm. So you mentioned one point that the write latency when you introduce a messaging system decreases rather than a relational database. When there is a relational database, the write latency is more than that of a messaging system. This is what you mentioned initially. But my question is, so for example, if you are using messaging systems like Kafka, mm-hmm. And when you talk about acknowledgements, so what kind of acknowledgement do you want? Do you want the acknowledgement just writing to the leader, or like writing to the leader and all the slaves? Because when you talk about getting acknowledgement about those stuff and then comparing the write latency to a RDBMS, is there any kind of statistics which prove that the write latency using a messaging system is less than that of a relational database?
So, good question. So the acknowledgement I'm referring to when you are handling a message to a messaging platform, let's say Kafka is a good example, is the knowledge that at the point you are sure the message is not going to be lost. So the message has been received by one node and replicated. You're right, a single write, in this case, to a single record, to a database, is not going to take longer. The point with the database, with the relational database, with the write in the relational database, is concurrency. So concurrency and locks block each other. It's not a case, I don't have the proof and don't have the numbers, but it's not a case all the big systems that have to write fast, forget about event sourcing, are eventually consistent. It was Amazon, I don't know if Amazon was the first, but Amazon invented what there was before DynamoDB, as they have to write and do not lose the things added to the basket, to the shopping basket. When you have to scale, the point is, when you are scaling out, when you have multiple nodes, not one single, you don't have to think about one single database, but you have to scale out, so you have to have a cluster of database, a cluster of system. To make this transactional, it's not just one write. This has to be some form of two-phase commit between the nodes, and this takes time, and this is going to be it's going to be slower than passing a message to a messaging platform. At least as passing a message to a messaging platform, even if the messaging platform is writing, this writing is append only anyhow. While the database is trying to enforce consistency. So every node has to talk each other to make sure nothing went wrong. Every node has to confirm the transaction, get back and confirm, and then acknowledge. While the messaging platform, usually it's quite smart, has been designed for doing that job. So it receives the message, replicates, you may decide the strategy, you may decide the replication, and you may decide when the acknowledge comes back. But unless you do something stupid, the default setting is usually one node has received the message has been replicated, the message has been, well, possibly written to the disk of one node, or not, but it's at least on two nodes. At this point, you get back in the knowledge. This process here is getting less time than writing to a cluster or database. If you have a single database, a single Postgres, it's probably faster, unless you're hitting the same group of records concurrently. In that case, the time could grow up a lot. All scalable systems are asynchronous and eventual consistent. Eventual consistency is asynchronous by definition, as consistency, here I'm talking about data store consistency, not the event consistency, different idea. It's still eventual consistency. Consistency happens later at some point. And this has not been done by chance. It has been done exactly to be able to scale. As you delay, it's not different. It's not okay, I was saying, the mindset switch is like switching from ACID transaction to the base. Base is the logic this kind of data store works. And this switch of mindset for data store has been done exactly for scaling. To be able to write fast and think later. I mean, they didn't use this wording, but DynamoDB, Cassandra have been designed exactly with this in mind. To be very fast in writing, not necessarily in reading, you have to optimize for reading, but this is a different problem, could be very fast. But to be very fast in writing and not losing the data you send in, if you set up the replication and consistency correctly. This, again, do not think about a single node. In a single node, if you have a Cassandra cluster and a single Postgres, and the single Postgres node is enough, you probably don't have this problem. If you have to scale out, well, at some point the relational database stops working. Of course, things like Oracle could be clustered. But in that case, be sure transaction becomes slower and slower. As the single node of a cluster that get replicated are distributed, there is latency between the nodes, and you have to keep absolutely global consistency, transactional consistency across all the nodes of the transactional database.
Okay.
While in the other way, and I'm using the example of this distributed data store as modern streaming platform like Kafka works exactly the same. They have a different job, but the logic behind Kafka is not different from the logic behind Cassandra. They are doing different jobs, of course, and their work is different, but the logic is kind of the same. They receive the write, they receive the message. One node writes on the disk or keep temporary memory, but temporary replicate to another node, at least one other node, possibly yet another, get the knowledge of having propagated the write, so you have multiple copies of the write, either the message of the write to Cassandra, and then acknowledge back to the client, okay, I got it, I'm not going to lose, unless, of course, I don't know, 3 nodes explode at the same time. Okay, it's a measure. You may make it a bit stronger, but the probability of using all 3 nodes.
Follow-up question. So after you have explained the whole CAP theorem,
no, I finished, sorry.
No, that's fine. I mean,
makes sense?
Yeah, that makes sense. But it's hard to visualize, because even if you talk about two-phase commits, it's hard to visualize unless there is unless somebody somewhere shows some statistics that writing to Kafka and getting acknowledgement from all the nodes takes lesser time even in a clustered environment.
It's never all the nodes. It's 2-3 nodes at most.
No, but you can configure Kafka to give you acknowledgement either from the leader or from all the nodes.
It's kind of overdoing. I mean, if you are replicating to 3 nodes, and you have, well, depending on how many nodes you have, in a reasonable cluster you have 3-6 nodes, and so what are the chances of losing all 3?
So it's the real question, are relational databases faster than NoSQL-like solutions, or?
Sorry.
I mean, the real question is, I have seen and read at a lot of places that messaging systems, writing to messaging systems is faster than writing to a relational database, even in a clustered environment, but are there any actual statistics?
Yes, this is why the whole industry moved away from relational databases. So no, they are not going to survive in the internet scale environments. So, but we can talk offline if you want to go into that detail. Any further questions, preferably in the back, because I'm here right now. Yes.
Yeah.
Hey, thank you. If I understand you correct, there are several ways how you can fight against inconsistency between read model and your source of truth, but all of them is about delays. And of them, yeah. The problem with delays is that the number, how long you can wait, it's about your domain. So probably in some cases, you need very short delay, shorter than it's possible because of network problem or even programming problems because somebody create bugs and etc. So is there any way, any ideas from your practice how you can fight against inconsistency in this way? So
the problem, you're right, you always have delays, more or less, and that is the point. The point is, when you have any distributed system against consistency and latency, so, well, delays, latency is the opposite of delay, are competing requirement. So you can't have something completely consistent with short latency, with no delay. You can't have it. So, of course, you will meet some legacy enterprise architect. Any enterprise architect in the room? Rotten tomatoes coming in. That will say, no, no, no. Everything has to be transactional. It's going to be distributed as we have terabyte of data and million of requests per second. Has to be distributed but transactional, globally, and under millisecond delay. Okay. It's not going to happen. They are competing. The point is, it's always a matter of balance, of course. You have to find the right point of balance in terms of, well, the technology you're using or the effort you're making in delaying and rebuilding, for rebuilding your consistency. You might even be slightly smarter, like, okay, I tried delaying less, and then I have some strategy for rebuilding the read model if I receive something that is contradicting what I built. The example are late events. They are quite easy to manage, as you just record the latest event you received. You received the late event if you have a reliable event timestamp, and you receive a late event, and you say in that case you haven't delayed the main read model, or you have delayed for less. At some point you received after minutes a late event, and you say, okay, this actually happened first. Okay, let's rewrite the read model, not the entire read model, the state of this aggregate, rebuild just it. This is a strategy for reducing the global delay and handling on demand some possible inconsistency. There is no absolute solution to the problem. Again, it's a balance. You cannot have both. You cannot have a transactional system, totally consistent system with short delays.
Isn't that the advantage of event sourcing? Because you can rewind, right? You basically make a hypothesis and then you find out, oh, there is some news which I have not taken care of. Mm-hmm. Let's start from 1 minute ago and let's recalculate the whole thing.
Yep. No, this is absolutely general. I mean, many things I said works for event sourcing in general, not specifically for the second approach. So the only thing is, if you are enforcing consistency when you're writing, effectively your inconsistency means rejecting one command. And in some cases you cannot do it. So either you stop enforcing consistency, so pass through all commands, effectively they are events, you're storing them, or you enforce consistency, and that's the idea behind. But yeah, many of the idea of being able to rebuild the models is not something related to this approach, event sourcing. It's absolutely general. The idea that the event log is a source of truth and you may rebuild the model at any point, this is event sourcing in general, any implementation of event sourcing.
Do you know some details about the underground examples that you made, like the London Tube?
Sorry?
The London Tube example.
No.
So when they do like guesses, so you've got 4 points, etc., and the fifth point between node 2 and 3 is missing. Mm-hmm. So this guess could be quite expensive. So if I've got a lot of cases where we have to guess, then it's going to take a long time. And what do they do if there's a high percentage of misses? So like if I get billed £10 more per month, I would be not that happy.
So I don't know. The only thing I know, I haven't worked with them. Okay. I'm a user. So what I see is, as a user, I see how many times they miss something, how many times they guess. It's not so expensive, as they are just doing, let's correct me. It depends. Okay, this is, I don't know how they implemented it. What I saw is, if commuting is very regular, their guesses are seldom wrong. If your commuting changes day by day, their guesses are sometimes wrong. And the point is they reverse the problem on you, so they charge the maximum of the thing. But okay, that's not about the implementation. It's a company. They are trying to make money. I don't know how they implement it. No. I have never worked with them. Again, I'm just a user. Usually I check, there is a log online if you are registered. You check the travels and sometimes you see something terribly wrong. You may apply for a refund. And so you may say, oh no, actually, you guessed I travel so far, but I get off here. And they usually say, there is the principle of trusting the user that is not lying, exactly the opposite that what happened in Italy. I don't know here, but in Italy happens. Usually the idea is the user is trying to steal, so let's charge the most, and you have to positively demonstrate you travel less. But that's a different thing, a different problem.
Yes.
If there's no question, it's just for my curiosity. I lost you a bit, I think, on a slide 24, and then. but then I catch you again. But no, no joke aside, on a slide 24, I lost where you are going, but then you sort of ditched the whole idea. So because you were going back into now, I want to do aggregation check on write, and what I felt was that you started with a problem, you went all the way in a circle to solve that problem, and you came back to the same problem. But then I was hoping that now you say something. So why did you travel all this path? And then you said, okay, so forget about writes, and you never got back to it. So I see that it's maybe not relevant. You just wanted to tease us, but in my mind I'm thinking that, but you must have really gone that way. So why did you go through this path?
So I had to jump between read and write to set up the scene necessarily, to put all the actors in place. I didn't get back to the same problem. I moved the problem. So I moved the problem of inconsistency to the reads, where I have the time of fixing it, while in the writes, I don't have the time of fixing it.
No. So
what was?
Yes. So what you had, that's why I tried to remember the slide. That you basically wanted to do a consistency check on the writes. Okay. So that's where we went. So immediately I was thinking. So basically, you're telling me what SAP HANA is doing, and then you, for example, talked about in-memory databases. But if I'm going to rebuild the state of my aggregates, which if I'm in a nice system, they are basically the objects I care for. I'm back to writing in a consistent database. Now, whether I keep the state in my memory or not, actually I'm making more trouble if I don't see it as a database and rather as my services, because now I have microservices that are stateful, the state is distributed. Now if I lose, so suddenly sort of many of the principles that I was thinking that, okay, they're in place, they were falling apart, and then you forgot about it. So
No. So there are different things here. The idea of the first idea of having the aggregate receiving comment and emitting, and the stateful aggregate receiving comment and emitting events. This is I oversimplified it. There was no time of explaining it in depth. This is the domain-driven design implementation of event sourcing. And this aggregate here is something that is in memory by definition. Okay. What I'm writing in the database, it's always, in both implementation events, it's event sourcing. I'm writing events. Append only, all of them. Then I'm rebuilding something accidentally from these events for serving the reads. But this is a secondary thing. Could be in memory. It could be a relational database. But the point is, I was saying, this is conceptually weakly consistent. I could drop it and recreate from the log at any point. And this is the idea behind event sourcing. The event sourcing also has other advantages. I don't want I could spend more time on the event source in general.
So the reason you did all this was to
Yep.
eliminate your write delays. If you go back in to do the consistency check in the distributed state of all your services, so that you always have for all your aggregates either an in-memory state of the aggregate that is consistent, which means you do even more checks than just dropping them into the database, or if they are not there, you have to rebuild them, which means that now you are basically recreating a modern in-memory database. So why not also write them in parallel to an event database and to your database and forget about this recreation of the state in the middle? Because you will end up with more cost in terms of write.
No, the point is, in the first approach, you have to have the consistent state to emit the event, and you're storing the event. You cannot store anything before you decided that the command was consistent. The change the command was causing to your in-memory state was consistent. The change moved the aggregate from the state A to the state B, and it's one thing in one node in one service was consistent, and then the state changed, and the change is represented by this event, and you store this event. I don't know if event sourcing also has other advantages, to be fair. I've skipped them. So,
Eventually.
I can.
I believe if you store the event as a source of truth and you store it in a separate database, you will get inconsistency there, because then you have a distributed
You're not
transaction.
storing in an additional database.
Yeah, this was the question, wasn't it?
Yeah.
Why don't you store the state also?
I think I didn't manage to communicate. The question was not for the second part of this presentation, for the motivation part. You went from, I just write to a database and this is slow. So
Okay, in the usual approach.
But then I also check the consistency. I keep state of all my aggregates in memory. If they are not there, I rebuild them. This is slower.
Yeah.
That's my point. So in a loop, you went from, oh, I have a problem, I'm going to solve it, and you made more problem. You ended up with the stateful services. You ended up with basically your implementation of an in-memory database. And then I wanted to know, so why did we talk about all this?
The point is, event sourcing has many more advantages than just this. My point was, the first step, the in-memory stateful thing, is the usual approach. And my point is, that doesn't scale. I would say 90% of the people doing event sourcing is doing that way. It's not wrong, absolutely. It works perfectly in many cases, but it might not scale if you have to cope with huge
and there are a lot of optimizations you can put in place there. So this was the naive implementation, and there you can put a lot of optimizations in there to make this system also faster, especially snapshotting on when replaying the events and things like that. But in essence, there is also a limit to scale because you have the single writer concept there. So you won't get around that one, and you get around this if you don't do anything on write, if you don't keep state around. So this is...
No, I reckon in this presentation, well, given the time of any presentation, introducing very fast the normal event sourcing. So if someone is not familiar with the common approach to event sourcing, could be a bit puzzling. This was a kind of bet, to be fair.
But we had plenty of meetups where event sourcing was also explained, so you can go back on the Microservices Meetup YouTube channel and watch those old videos. There you go.
Okay.
I think I'm missing in communication. That's why I remember the slide so that you go back there. So my point was the story that
I have a suggestion now, because it might be that we are going deep into a topic. We grab a beer and we just look at the slide and go into depths how to optimize this scenario, and then we might get a second presentation out of this one. Any additional questions? No? Yeah. Oh, there.
I have a question regarding the thing later part. do you use any frameworks, tools for this part? I know there are many tools, but what do you personally use, and how to handle multiple partitions, etc., multiple readers, to scale the things on the think part?
Okay, this is more a platform thing. As well, from the event sourcing point of view, there are many frameworks doing the other approach, the first approach. There is none, as far as I know, using this approach. From the scaling in and out, and routing and so on, it depends more on the platform. So it's a normal scaling problem. Scaling of the data store, it's a problem of the data store itself. Scaling of the nodes, it's well, you could use the auto scaling of AWS or so. So it's not something specifically related to this problem. And the routing I was describing is not something specific. That kind of routing is done for the usual implementation of the event sourcing, is done by the framework Axiom, I don't remember. There is one famous one doing that kind of routing and locking, but my point is you shouldn't have to route. So if you're using the second approach, you're not routing anything. You just receive, you have, I don't know, 10 services receiving writes, and the requests, the events come in and get processed by any nodes. And the point is avoiding this kind of routing. If you have to do that kind of routing, it means you're using the domain-driven design approach of the event sourcing, and then the framework doing that are doing usually this kind of routing, or other approach like global locking or optimistic locking. Specifically, well, for scaling in and out, this is a platform issue, so depends on what platform you are using. I mean, it's a normal problem. I mean, you have 10 nodes, when CPU grows, you scale out.
I have two questions. A very simple one: are these slides available afterwards? Okay.
Yes, I definitely send them.
And the second thing is, you use the term IoT in your title.
Yeah.
But I missed that in your presentation.
It was when I was talking about the possible domains where this approach applies.
Yeah, okay, looking at the requirements for IoT sometimes are very time critical, real-time dependency. And that's what thing I'm missing, because you cannot delay it to days or something like that. As an example with the tube stations. That's one thing, and the other thing is, which also gives you a lot of computing efforts to check if the message is lost. So normally in IoT you have a repetition rate, at the server side. So, but now you have to check if all these devices you are writing, you are collecting, is there one which I am missing? And that gives you a lot of efforts. You have 1 million devices, and you have to check that all are in sync.
Okay. If your IoT are not necessarily, to be fair, real time. Maybe there are in many cases, if you have to be real time and you have an unreliable network, I wonder how you make it. But okay. But if you have to be real time, you cannot use any form of event sourcing, and so it's a different problem. And if you have to be real time, maybe you're driving the process, you're not just gathering data. Isn't that the case? Okay, so maybe if you have to be real time, your specific problem doesn't actually fit very well. And I reckon this. The second part of the question was
to check the consistency of your data.
Yeah, it does require effort, but again, it's a consequence. If you are in the condition I was mentioning of not paying. You cannot rely on having received all the messages. And the goal of your system is building a picture, a consistent as possible picture of what happened in the devices. And you don't know if you missed some of the messages. The point is, the only place you can do this effort is later, when you rebuild the picture of the word. That was my point. And so I think we are not talking about the same thing. So IoT is a very general thing, I reckon. This doesn't apply to everything in the IoT. This applies where in the domains where you're gathering data, things that have happened, and you're making the picture of things that has happened.
But isn't it regarded more or less an offline system? If you have enough time for a delay.
Yep. Well, it could be seconds. It's not. I was saying the example of the TFL, it's hours, could even be seconds. But anyhow, if you may even decide to forget about the simplest implementation is forgetting about the missing events. Yeah.
But that's a real point. It checks that everything is happening in the world. Doing some updates to the world.
I'm not sure we are talking about the same. So
let's take this one offline. So now we have a true IoT problem, and we have an event sourcing optimization problem over beers over here. And you will stay around, so any further question, just come up front. I believe you need to grab a beer before that. And I've seen in the meantime, we also now have cold pizza, which is a great thing. So grab some pizza, some beer. Thank you.